Dependent samples t-test, the last of the t-tests. When do you use it? When you have correlated samples. Now, for you all, this means a within subjects design. It can mean a matched pairs design. Essentially, any case where the observations are coming from, are connected somehow, whether maybe participants in group one are brothers and participants in group two are their sisters, right? Then we would use a correlated samples design. When we match people on like some variable, maybe we match them on socio-demographic variables, right? We have one person with all these socio-demographic variables who's matched in the second condition as somebody with the same socio-demographic variables. That's another case. But most of the time, we are talking a within subjects design. So here's the data I will be using, and the example is how do faculty bowl when students tell us nice things versus when students tell us mean things. And I want to point out that the one sample t-test is literally that the dependent samples t-test is just a one samples t-test for the difference scores with a comparison mean of 0. We apply our MAD outlier detector just as normal. We check for normality in our own data. We state our null. I am trying to statistically disprove that the true population mean of faculty bowling scores when students are nice minus the true population mean of faculty bowling scores when students are mean equals 0. We're going to gather all our known sample descriptive statistics. We are just going to get these from SPS, but the important ones, both means, the mean difference, both standard deviations, the standard error from SPSS, the degrees of freedom and N from SPSS. We can find all this stuff. The 95% confidence interval of the mean difference, all from SPSS. Then we have to draw a random sampling distribution of mean differences if the null hypothesis were true, and we have to do our p-value problem. This is the same thing we did in last class, so I'm just going to go over it one last time. The shape of this distribution, it's symmetrical t. The degrees of freedom adjust this shape. That's why we have to put them on the graph. The standard deviation of the random sampling distribution of mean differences is called standard error, and this affects the shape. It makes it flatter. We know that. Limits negative infinity to positive infinity. If the null were true, the most commonly sampled mean difference would be 0. So this is going to be the point at the peak of our curve. We know this. We get this. Let's move on. How do we calculate degrees of freedom for a dependent samples t-test? Well, number one, you have to realize that we don't have two samples of scores. We don't have two samples. We have one sample of difference scores. That's really important. It's a really important click in your mind that has to be made. You have to make that click. I know it looks like there are two samples here, but really it's one sample of difference scores. So now our question is, how many of these difference scores are free to vary and still result in the mean of these different scores that we sampled? So it's really that same riddle, right? Like, we know that we have a group of 10 observations in this example. We know that our mean of our different scores is 15.7. We know that from the previous slides. How many of these 10, theoretically, how many of these 10 different scores are free to be any number in the world? 9 of them. How many must be fixed? 1. Because that one that's fixed allows us to make sure that our sample mean is always 15.7. It's the same idea as before. It's just now our sample mean that we're interested in is a mean of different scores. So how many of the different scores are free to vary? N minus 1. I'll show you this in class. I know it doesn't completely make sense, but I'm going to give you some fun little riddle problems. And then we know that our degrees of freedom change the shape. And we know that our standard error makes it flatter, like I said earlier. And then we have to add our mean difference or the mean of the difference scores, which these are equivalent to the curve. And then we do the same thing. We add our mirror image of our sampled mean difference to the curve because we always do two-tailed tests. And we add the shaded area we're looking for because this is what we're trying to solve. So our problem that we're trying to solve is right here in picture form. We want to know the fraction gray area over white. Now just realize that there is white under the gray area, so our white area is the entire bell curve. Gray over white, gray is what corresponds to our p-value, right? That's what we're trying to figure out. Gray over white, that equals our p-value. Now, we sampled a mean difference of 15. The definition of the p-value is the probability of sampling a mean difference has extreme or more extreme than the mean difference we sampled if the null were true. Well, 15 points, a mean difference of 15.7 and a mean difference of negative 15.7 are both equally extreme, and more extreme means go all the way to the tail. So we are just trying to figure out the gray area over the white area. That's our probability problem. Nothing special here. Now we just calculate our test statistic, and this is our t-score. So our t equals our mean difference divided by our standard error of the difference scores using our sample formula of standard error, the thing we used a long time ago. And what do I mean by that? Well, that's literally 15.7, our sampled mean difference, divided by our standard deviation of the difference scores using the sample formula. You can see that there. That just means divide by n minus 1, not n. Divided by the square root of n, because standard error is always standard deviation divided by the square root of n. I let SPSS do that calculation for me, and I put in my descriptive statistics. So 15.7 divided by 7.2 equals 2.18. I have recently received a lot of questions where folks are confused on the interpretation of t. And, I think I was confused too until you really made me sit down and think about it. So I appreciate the questions, folks. So let's just talk about it in simple ways. So this picture right here represents the distribution of all possible sampled mean differences if the null were true. Standard error is just the standard deviation of this distribution, right? That assumes the null is true. So in this case, our sampled mean difference of 15.7 is 2.18 standard deviations greater than the predicted mean difference of 0, which is predicted from the null being true. So our mean difference, our signal, is 2.18 standard deviations larger than the expected signal if the null were true. That's it. That's all it means. That's all I'm going to say. But essentially, it's a Cohen's d in the distribution, assuming the null is true. So it's sort of like our calculated signal is 2.18 standard deviations larger than the predicted signal that we got from assuming the null is true. That's it. Solve for P. Let SPSS or PSPP do this for you. You can do it by hand. It's identical to how we did it for the one sample t-test. We just assume our comparison mean is 0. It's identical, but you know what? At the end of the day here, let's use our programs. They can solve for P for us. When I use those programs, I find that our P is 0.06. I fill everything out here. This is our problem. We have it solved. We know our p-value is 0.06. Gray over white. Gray is 0.06 over white being 1. So it's it's 0.06 over 1. 0.06. That's all it is. So we have 6% of 100%. So the probability of sampling a mean difference has extreme or more extreme than the mean difference we sampled if the null were true is 6%. P is greater than 0.05. It's close, but close is only good in horseshoes. So we know nothing. We're going to use Excel and get our two graphs. So then we just write up our results. I modified Lakens results from the effect size calculator because I find them to be really good. But essentially, I would write faculty bold better when treated well by students. And so this is the mean of when faculty are treated well. Mean equals 136.7, standard deviation equals 81.84. Then when students treated faculty poorly, mean 121, standard deviation 66.62. T, degrees of freedom, with 9 degrees of freedom equals 2.18. Our p-value equals 0.057 or 0.06. Our mean difference equals 15.7. The 95% confidence interval of that mean difference equals negative 0.58 to 31.98. Cohen's d equals 0.69. The 95% confidence interval of that Cohen's d equals negative 0.02 and comma 1.40. See figure 1. These results indicate a potentially large effect where Bolling scores of faculty are reduced by student meanness. However, our estimation of this effect is poor, and we need to run a better study to examine if being mean will reduce Bolling scores for our faculty. See figure 2. Figure 1 would just be our mean difference from the Excel file, the bar graph. Figure 2 would be our 95% confidence interval of the mean difference. Or if you want, you can modify it to be, you know what, I'll just make sure that the graph maker has that in there. It could also be the 95% confidence interval of the Cohen's d's. So I'll just modify our graph maker for that. Now, ultimately, this is all you would have to publish. Those two graphs and all these words right here. All the thinking that we've been doing results in 2 sentences. And so I know it's a little like, well, why are we doing all this? Because you need to understand what's going on. A lot of folks can write down their p-values. They don't know where it comes from. You know it's that color fraction. I love that. You all have worked so hard. And, you know, I can't say how much I love this class and how much I love teaching you all. Okay, so first step number 1 is check for outliers, normality in your own data. So with this first step is we enter, our raw scores are actually our raw difference scores, and we check for any outliers. I just plugged them in there. And we have no outliers. So everything was great. There's no outliers. So, you know, I don't have to mess with that. I like when I don't have to mess with that. But there we go. That is done. Okay, so we're in SPSS, and we want to just run our data, get our descriptive statistics, get our p-values, get our t-scores, do all that stuff. All that stuff. That's the first step I do when solving one of these problems. And that's relatively easy. I entered the data. That's no big deal. I have Bolling nice, Bolling mean. You can see that, right? By mean, I mean actual mean tendencies, not the average. You're mean to us, okay? And I'm like, okay, analyze, compare means, paired samples t-test. I highlight both means. I throw them in there. I don't have to click any options. I click OK. I get the output. I get everything I need, the means, the standard deviations. This we'll need for our Cohen's d, this 0.974. We need to enter that into that Excel file, but just hold back. Our mean difference of 15.7, even though it calls it the mean, notice over here, it's a mean difference, right? Standard deviation of the mean difference, standard error of the mean difference. 95% confidence interval of the mean difference. T-score, degrees of freedom, p-value. Now, I've been saying throughout the lecture that this is just a one sample t-test of the difference scores, comparing it to a mean of 0. So let's compute variables. Let's call it difference scores. Nice mean, nice minus mean. I literally do label things this way. I like to never have to worry about going into a data set and not knowing what's in there. So I just have these ugly labels that if you read them, they tell you what's in it. So here we go. I click this difference score. It creates the difference scores for me. Analyze, compare means, one sample t-test, throw in my difference score. My test value is 0. Click OK. And what you'll see is I get the exact same t-score, exact same degrees of freedom, exact same p-value, exact same mean difference, exact same 95% confidence interval of the difference. What I don't get, I do get the same standard error of the mean difference, standard deviation of the mean difference, same n. What I don't get are these right here, these sample descriptive statistics. So always use your dependent samples t-test on that paired samples option when you're using SPSS or PSPP. But I wanted to show you that these are equivalent. I've just proven that. Yay, math. All right, so currently when we run anything in PSPP, hopefully I didn't change anything. G.I. Joe program. We know how I feel. I love it and hate it at the same time. Whenever we run a data analysis in PSPP, it only gives us 2 decimal places. So compare means, paired samples t-test. I click OK. I got to get out of this because it's maximized. So now I should have, you can see this, right? And this isn't great. Particularly, it's this value in the future that's going to mess up my Cohen's d calculation. So I figured out, I didn't know how to do it before today. I Googled it. I think that's important. I Googled how to change the number of decimals in PSPP. I found this website right here, and it said use this formula right here. So set format F22.6, that's going to give me 6 decimal places. So I'm just copying that in. I'm going to PSPP, and I'm like, okay, I'm going to leave that there. I'm going to go File, New Syntax. You can do that anywhere, but I'm just going to do it from my data. File, New Syntax. I'm going to paste that in there, and if I click 6, if I wanted 4 decimal places, I would put 4. If I wanted 3, I would put 3. If I wanted 9, I would put 9. I'm going to put 5. And then I'm going to click Run, All. And you'll see it says set, so that's set. And I want to just delete this if possible. Actually, I'm just going to close. Analyze. So now it's like, okay, I set that. And I want to run my analyze, compare means, paired samples t-test. So in this data set, I just have bowling when nice, bowling when mean. You got to click it in one at a time. The options aren't important. I click OK, and I'm looking for good. I have stuff reported to 5 decimal places. This is important for calculating the Cohen's d. Now, when we look at this, this is the same output that we got for SPSS, and that is great. I don't know why it didn't give me 5 decimal places for the significant value. There's probably some other variable, but it doesn't matter. That's not the one I'm worried about. I was worried about these values here. But that's essentially how you do it in PSPP. So start, is it a t-test? Yep. Is it a comparison between correlated samples? Yep. Do we have all the data? Yep. Have I put it in already? Yes. So, I have it all in. But first, my first mean is 136.7. If we're going to PSPP, we can see where all this data comes from. I get these 2 means, I put them in there. I get these 2 standard deviations, I put them in there. I get this number of paired samples, I get it in there. And I'm going to have to put this correlation in there, okay? So I'm trying to open these up so that they're overlapping. I'm going to click PSPP again. Hopefully I can get them to overlap, and I have. So right here, it's like, let's just double check. Let's just see what happens. Oh, too many windows open, but we're back. All right. Actually, I'm not going to share that. We're going to start now. We open up our calculating effect size. I'm going to start. Calculator, opening our calculated effect size file. Start here. Is it a t-test? Yes, it is. Is it comparison between correlated samples? Yes, it is. Do we have the mean standard deviations correlations? Yes, we do. And then we have to enter in those means. So 136.7 came from there. And I'll just check my data. The standard deviation of that distribution, 81.84. 81.84. I then, number of pairs, there are 10. My second mean, 121 perfectly. 66.61665. 66.62. I'm okay with that for this part. Now right here, my correlation is 0.97373. 0.97373. That you have to type that in there. Even though it shows up as 0.97, if you don't, that messes everything up. One of the great things now is I can check, does everything match up? Do I have the same t-scores? 2.18, degrees of freedom 9, p-value 0.06, 0.057, basically the same, right? So I know everything's good based on that. Now I'm going my 95% confidence interval of my mean difference, negative 0.58, 31.98. That's good. My mean difference was 15.7. My mean difference here was 15.7. That's all good as well. My standard deviation of the mean difference, my standard error of the mean difference, my standard deviation of the mean difference, my standard error. That's beautiful. My Cohen's d then is 0.689 or 0.69. So I need that. It's this line right here. It gives us other things. We're not going to worry about those. And then I had to create my own 95% confidence intervals of the mean difference. So I'm just going to write lower limit for d. Well, I'm sorry. I had to create my own confidence intervals for the Cohen's d. So this is my 95% confidence interval, Cohen's d lower limit, and my 95% confidence interval, Cohen's d upper limit. So how do I calculate that? Well, first things I think is cool is just to step inside the equation for Cohen's d. The mean difference by the standard deviation of the different scores. Perfect. So all I have to do now is for my lower limit, I'm going to look here. Oh, this is my lower limit. So this equals the mean difference of my lower limit divided by my standard deviation of my different scores. Very perfect there. This equals the same thing, my upper limit divided by the standard deviation of my different scores. Boom. That's my 95% confidence interval of my Cohen's d. And from this, it's like, it's real. We see a very large Cohen's d, but my estimation of it is a little off. Worst case scenario, there's a tiny effect in the opposite direction from what we found. So that means in this case, maybe your scrutiny could increase our bowling by a tiniest amount. Really, that's really a no effect. But since it is the opposite of what we found, it's a tiny, not important, not barely there increase of 0.02 standard deviations. That is so tiny. Best case scenario, right? Your meanness reduces our bowling by 1.40 standard deviations. So the thing about interpreting a Cohen's d is you have to know what your two means mean. So we bowl better when you're nice than when you're mean. So you could say being nice to us increases our bowling by 1.40 standard deviations, but your goal isn't to increase bowling. Your goal is to decrease bowling. So you would say like being mean decreases our bowling scores by 1.4 standard deviations. That's the best case scenario. The middle case scenario is that your meanness decreases our bowling scores by 0.69 standard deviations. So don't just assume the numbers are gonna make sense for you. You got to take a step out. You got to say, oh, they did worse when we were mean. Okay? All right. And they did quite a bit worse when we were mean. Particularly basically 0.7 standard deviations worse. So a medium effect size, right? And when we get our 95% confidence interval of the Cohen's d, we get that we're 95% confident that the true Cohen's d ranges somewhere between negative 0.026 and positive 1.40. So worst case scenario, there's a tiny effect where you're improving our scores with your meanness. Best case scenario for you all, you're reducing our scores a lot by your meanness. But essentially, that's our Cohen's d of the confidence. Those are our 95% confidence interval of the Cohen's d. This tells me that I need to run a better experiment, right? I don't have a solid estimate of the Cohen's d. The middle of that estimate suggests a large effect, but it could be anywhere from a tiny effect in the opposite direction from what we want to a massive effect in the direction of what we want. We need to run that. We can run the study again. We can do it 2 years in a row and then get a better estimate with a meta-analysis. I won't talk about that, but that would be the way to go. Or we could hire more faculty. That's my choice. We need to hire more faculty to get a better estimate of this effect. Or we can just run more trials. We can bowl 8 games, 4 of them you're mean to us, 4 of them you're nice to us, and then we just deal with all those headaches. But at the end of the day, this is how we calculate our Cohen's d. All right, so now we're to the point where we need to create our graphs, and I've expanded it to show you the 95% confidence interval of the Cohen's d. So essentially, all we do is plug in our numbers, mean of group 1, these are from SPSS, mean of group 2, standard error of the different scores from SPSS, number of different scores from SPSS, your known population mean labels, nice, that's when you're acting nice to us, unpleasant when you're acting mean to us, the effect of niceness on faculty bowling, that's our title, horizontal axis category, student behavior, nice or unpleasant, faculty bowling scores are dependent variable. I'll walk you through what's going on here. It's calculating, it's just copying the standard error from SPSS. It doesn't actually have to calculate anything. It calculates the mean difference for us. We get our t-score. We can see that's the same. It calculates our Cohen's d. I round it because I'm going to put it on a graph, so I round it to 2 places. This is just the formula that I need in order to calculate 95% confidence intervals. Essentially, like, it's determining my cutoff values, essentially. Don't worry about it. I just needed that to make these numbers happen. Down here, this is the same as it always has been. This is just finding a 95% confidence interval, the mean difference. So that's the same. Okay, all this is into this graph. Then from that, I had to calculate upper and lower limits for my Cohen's d. So I used the formulas, right? You don't have to worry about these formulas, but you can see what I had to go through to make this happen. It's a little bit, it's a little much, but essentially all I did was I took my standard error, and I got rid of the square root of n on the bottom by multiplying the whole thing essentially by the square root of n in that denominator. It's a little complicated, but you can see it here, right? I take my mean difference divided by my standard error times the square root of n. That's essentially all that's going on there. But that gives me my Cohen's d's. I round them down here. And this right here just uses logic to choose which one should be on the left and which one should be on the right. So I'll choose one of these two to be on the left and right. So in this case, this is choosing which one's on the right, which one's on the left. And this 0.69 is coming from up there. So now we have all of our graphs. We can see that when it looks like there's a difference, but there's not, right? When you're nice to us, we bowl a little bit better when you're mean, but that's not a significant difference. Okay. This is why I hate these graphs, right? These graphs are just pretty worthless in my opinion. To make these graphs look like the significance that you're used to. No, actually, those are overlapping. Don't worry about it. Yeah, they're not significant. We can make it bigger to see that. But the graphs are being made for you. You always create these graphs. Oh, when we're nice, they bowl better. That's why this graph is there. When they're nice, they bowl better. When we're not nice, they bowl worse. It's not significant. We can kind of see that those bars are overlapping enough. Nonetheless, it's no big deal. 95% confidence of the mean difference and the 95% confidence of the Cohen's d. That's your graph maker. If you're going to include one of these two graphs, include the Cohen's d. You have to include one of them. Include the Cohen's d one. This is the one that makes more sense. When I'm looking at this, best case scenario for you all, you're decreasing our scores by 1.4 standard deviations by being mean. Best case scenario, you are increasing our scores just slightly by 0.26 standard deviations. And I just want to double check that because I'm like, ooh, is that correct? So I'm going to go back to my Excel file here that I want. Not that one. I think it's just right behind us. Yep, sure is. 0.02, 1.4. So that's telling me I think I did something wrong. And now I got to redo this. What's going on wrong there? All right. So it's going to be in that. I see what I did wrong. So I think it's good to see how I problem solve mistakes. So what I noticed there was that my bottom I got to get rid of the square root of n in the bottom formula. But the way I did it by not putting in those parentheses just messed everything up. So I got my mean difference divided by my standard error times the square root of n to get rid of that. And once I click that, everything's fixed. And you can see it fixes it in the graph as well automatically. So I'm glad I caught that. That was really great. I'm glad you got to see my problem solving steps, right? When my spidey sense took off, I was like, whoa, something's not right here. Let me make sure, because I thought it was really small. Boom, it was. Then I'm like, why did it happen? I looked at my formula, found my mistake, and now you have a perfect graph creator. But yeah, I make these mistakes, in my life, but I've corrected them before you've seen it. But I'm not remaking this video. I am trying to get this out to you right now. And so we are done. All right, so I've done all my analyses, and now I'm going to finish my homework. Step 0, outliers. Use the man outlier detector. No outliers. I'm putting it on there, but it's step 0, so it can be omitted, but I'll notice if your data's wrong. Step number 1, state the null has a mean difference. So the true population mean of faculty bowling scores when students are mean minus the true population mean, that's what the mu's mean, of faculty bowling scores when students are nice equals 0. Or you could flip them. No big deal. I just put it in there to let you know. My descriptive statistics are all coming from SPSS or PSPP. So my mean when students are nice, my mean when you're mean. And I'm taking a moment. I'm like, oh, when we're mean, the faculty do worse. That's a good thing. Standard deviation of bowling when students are nice. Standard deviation of bowling when students are mean. The mean difference. And then I take a moment. I'm like, what's this mean? Oh, it's 15 points different, but I need to go back up here. When we're mean, they bowl worse. Do not let that leave your mind. Do not just write down the numbers. Know what the hell the numbers mean. That's the most important rule. And so that's why I wrote it there. My 95% confidence interval of the mean difference, again, from SPSS or PSPP. My degrees of freedom is 9. My standard error of the different scores is 7.20. So that's my appropriate standard error. I just put it in there. If you notice, I don't care about the labels here because it doesn't matter in the real world. What matters in the real world is the final write-up. Step 3, I'm calculating my Cohen's d from Lakin's Excel file and my little change to it. And I'm like, okay, what does this mean? This means that bowling scores when students are mean are reduced by 0.69 standard deviations in comparison to bowling scores when students are nice. This is a medium effect. If you notice, I've taken out the signal to noise thing. Let's get rid of that. It's true, but let's just get rid of it. Everything's signal to noise. Boom. You know what? It doesn't really matter. It's not the most important interpretation. These are the 2 interpretations I want you to do from now on out. And even when you're doing a one sample Z, you can omit those now. It was a learning process. I'm trying to teach you what's going on. And, we're scaffolded beyond it now. So, boom, it's gone. So we got this is a medium effect. And then we have my 95% confidence interval of my Cohen's d, which is negative 0.02 to 1. And this suggests poor estimation of the Cohen's d. Now, I don't quit this study. For me, whenever I have a Cohen's d of 4 or above, I'll at least run one more replication just to see if I should throw it out. I'm going to try to do it better. This is a small sample size. I'm going to try to do this study better, but I have bad estimation of my Cohen's d, just like I have bad estimation of my mean difference. I need to rerun this study to figure it out. Step number 4, I'm going to draw my random sampling distribution of mean differences for when the null is true and the p-value problem. Well, let me just see here. I like to make graphs and stuff on Excel, so I'm going to go into, not Excel, I'm sorry. I like to make graphs and stuff on PowerPoint. Not graphs, but figures on PowerPoint. There you go. Come on, DeRicky. We know you want to finish. We know you want to go have your weekend back. Let's just make it happen. Right here, I need all this in there, right? I don't care if you put the t-value on there. You know what it means. I'm not too concerned, and I'm going back to my Word document and I'm pasting it in there, and it's going to take its sweet time. Okay, boom, I'm ready to go. And then calculate my test from, got that. Observed mean difference is 2, and here's the new thing. You don't have to write this in there, but I think it's really important to realize that, my observed mean difference of 2.18, my observed mean difference of 15.7 is 2.18 standard deviations greater than the predicted mean difference of 0, which is set for when the null is true. All right, so what we're saying there is my observed mean difference is 2.18 standard deviations greater than the mean difference we would expect if the null were true. So that's all that's going on there. P-value 0.06. What do we know? This case, do we disprove? Do we disprove and reject? No. So I know nothing. Insert my graphs. I'm going to go ahead and insert those graphs for you here. I'm going to choose this one. I'm just going to copy it, throw it into my Word, paste it. That's figure 1. The one I put in first will be figure 1. And then I'm going to skip the mean difference one because the Cohen's d is much easier to understand. Going in here, throwing it in, second graph, boom. So just to reiterate, I'm 95% confident that my true Cohen's d is somewhere between negative 1.4 and positive 0.03. We can alter these around if we needed to. We can go back. We can change what mean is first in that Excel calculator. And maybe I should do it here, but honestly, this is good enough because it's telling me the same thing. When you see negative 1.4, negative 0.69, and positive 3, that's the same thing as seeing negative 0.03, positive 0.69, and positive 1.4. Now, what I think for me, for you all, this graph is better. So best case scenario, right? Your being mean reduces our bowling by 1.4 standard deviations. Worst case scenario, your being mean increases our bowling by 0.03 standard deviations. So that's why I put it in this way. But it's okay because none of this matters, right? You're like figuring it out. You're figuring it out. You got the right numbers. It doesn't matter if that's negative or positive. The thing that you publish to the outside world are these two sentences. Faculty bowled statistically better when treated well by students, mean standard deviation, than when students treated faculty poorly, mean standard deviation. I'm not the best writer. If you want to change up that wording, feel free. That doesn't bother me. I'm not hurt by this. If I'm going to actually publish this, I'm having my advisor, my wife, and one of my best friends look this over to make sure I don't have too many errors in it. Then I have my mean equals this, and my t-score with 9 degrees of freedom equals 2.18. My p equals 0.06. My 95% confidence interval. Oh, we can see, left out my mean difference. My mean difference equals 15.7 with a 95% confidence interval of that mean difference of negative 0.58 to 31.998. That's been all over this homework. My Cohen's d equals 0.69. My 95% confidence interval equals negative 0.05 1.3. I'll match it up there. I was a little off on rounding to 1.4, but that is, if you wanted to, you could make this negative 0.69, and you can make that 0, that positive and that negative. I don't really care. They're all correct. Both of those examples are correct. See figure 1 and figure 2, really. I could put them both there. See figure 1 and figure 2. But then in my next sentence, I say these results indicate a potentially see figures 1 and 2. That's how I'm going to do it. No big deal. That's good. These results indicate a potentially large effect where bowling scores of faculty are reduced by student meanness. However, our estimation of this effect is poor, and we need to run a better study to examine if being mean or unpleasant, if you want to write it that way, will reduce bowling scores for our faculty. And we are done, and this is a perfect score. This is a perfect test, and that is, it's been great, and I think you really understand what's going on, and I think it's pretty amazing. You're going to do the 10 steps for the following problem. Include, all the steps. This time, I want you to pull out the big guns. How do air horns affect our bowling scores? That's the real question. You can see, for me, I'm unaffected by your air horns. Your air horns do not bother me. But I think it's time you all started figuring out how to take down the faculty. What are you going to do? Use an air horn? I think that's the most extreme thing you can do. Let's see what happens statistically when you do this.